Hello everybody, so this is going to be on the natural logarithm. I'm going to be explaining what the natural log is, and I'm also going to be doing a couple of examples of the natural log as we go through. So I want to get right into this. Let's go. So the graph of y equals the natural log of x is a reflection of the graph y equals e to the x. So in the line y equals x. So the line y equals x, which means whatever y is, x also is. Okay? So the notation ln means the log of base e. So when we write logs, usually we'll write log, then the base of x, for example. Here, you can write the base, if you like, e of x, but typically that can be written as ln of x. Alright, it's just a bit of new notation. It is nothing that is important to you, but it is recommended that you do know what I'm going on about here. So log base e of x is equal to the natural log, as I've just written. We can compare the graphs of y equals e to the x and y equals the log of x. Alright, so 1, 0, 0, 1. Alright. These points here, alright, are symmetrical of each other. Okay. They are reflections of points. Alright. So, the graph of y equals log of x reflections. So you should use the natural log when solving exponential equations involving e. Now, I've not done exponentials in this playlist just yet, but I will do as soon as I get this one sorted. So, the question is, solve the equation e to the x equals 5. If e to the x equals 5, we take natural logs of both sides, which means we get log base e of e to the x, which is equal to log base e of 5. Using the power law, I can bring the x down to the front. We've got x log e of e is equal to log e of 5. Log base e of e is 1. So I've got x equals log base e of 5. And it's fine to leave your answer as an exact value, because log base e of 5, if you try that on your calculator, it's going to be incredibly long. And there is no point in doing that. Okay? So, there's this method as well. So if we've got e to the x equals 5 and take natural logs, get the natural log of e to the x is equal to the natural log of 5. Using the power law, we get x equals a log of 5. We use notation like the above when dealing with natural logs. Now, it is fine, you can use the method in red, but the method in the blue is a bit quicker because you don't have to write out as much. You don't have to write the base every time. So, you won't get marked down to the left hand side, but it is recommended that you use the right. Okay. So the next example is solve the equation the natural log of x is equal to 3. So if the natural log of x is equal to 3, think about what the natural log of x represents. It represents log base e of x equals 3. Rewrite without using the logarithm, we get e cubed is equal to x. So learn this pattern so you can basically use it. So if ln of x equals 3, then e cubed is equal to x. It's just a little pattern. So for example, if I had ln of x is equal to 2, then you could say e squared. So it's learning these patterns which can make exam questions a hell of a lot easier. Okay. Moving on. So the equation e to the power of 2x plus 3 is equal to 7. First thing, take natural logs. We get 2x plus 3 is equal to ln of 7. The reason why the e will go is because natural log of e, we know what the natural log of e is, which is natural log of base e of e, which is 1. So it doesn't change, so the 1 will basically get rid of. So natural log and e, because they're opposites of each other, they will cancel. Okay? I'm left with 2x plus 3 is equal to log of 7. I can subtract the 3 from both sides, so we'll get 2x is equal to log of 7 minus 3. Divide by 2, so we'll get x equals a half log 7 minus 3 halves. Okay, so solve the equation 2 log x plus 1 equals 5. Nice and easy, this one actually. We can subtract 1 from both sides, we'll get 2 log x is equal to 4. Divide by 2, we get log of x is equal to 2. Notice how I'm saying it's log of x. Okay, we don't usually say natural log every time. Just gets a bit repetitive, but as long as you know that means logarithm, then you should be okay. We write it without the logarithm if we like, and we can get e squared is equal to x. As I showed you in the previous example, when we had ln of x equals 2, we get e squared equal x. There's these little patterns that you can use. Okay. Moving on. Solve e to the 2x plus 5e to the x is equal to 14. So I want to subtract 14 from both sides. We've got e to the 2x plus 5ex minus 14 equals 0. I want to factorise or write using y to help. You can use that as well if you want. So say y equals e to the x and make a substitution if you like. So we get ex plus 7 times ex minus 2 equals 0. We've got double brackets. There's two possible solutions for e to the x. We've got e to the x equals minus 7 or e to the x equals 2. No solutions if the e to the x is less than 0. Less than 0, so no solutions. So the only solutions we've got is e to the x equals 2. We'll take natural logs, we'll get x equals log of 2. So, the next part of this video is going to be on reduction to linear form. Now, you might think, what the hell is going on here? Reduction to linear, what does that mean? That basically means I'm going to take an equation and put it into a linear format. So, in the format, when we say linear, you might think of y equals mx plus c, or y minus y1 is mx plus x1 maybe, if you've seen that yet. But it's using these ideas, taking a curve down to a line. It's quite helpful actually. You'll see we'll use it with natural logs, which is why I've put it in this video. Okay, so logarithms can be used to manage and explore non-linear trends in data. If you're familiar with problems involving straight line graphs, you can use logarithms to turn an exponential relationship into a linear one. In short, using a logarithmic scale can turn a curved line into a straight line. Okay, so I've got the curve here, y equals x squared. We should have seen this a lot of times. And we've got log base y is equal to 2 log of x. So these are the same equation, one with logs have been taking of them. Okay, so you can see all I've done is I've took logs of both sides on the one on the left. If it's plotted on logarithmic axes, it is a straight line. So this can be shown by starting with an exponential relationship, y equals ax to the m. Take logs of both sides, we get log base y equals log base a of x to the m. We separate using the addition law, so we get log base y is equal to log of a plus log of x to the m. So breaking it apart, using the power law, we can bring the power down. We've got log base y equals log base a plus n log of x. Compare this with a straight line format, y equals mx plus c. You can see that log of y is the y bit, as I've highlighted. The y term is the variable, and the mx is the n log x. We then have a constant multiplied by a variable, the n is the constant in this case, which is the m. And log of a is the extra plus c. And then we have the constant. Okay. It shows the rank by size and population of some UK cities. We've got Birmingham, Leeds, Glasgow, Sheffield, Bradford. Okay. These, I think, are in the Edexcel textbook that I took these from. The relationship between P and R can be obvious by the formula P equals AR to the M, where A and N are constants. So a scatter graph using this data looks something a little bit like that. Draw a table giving values of log of R and log of P to two decimal places. Part B, plot a graph of log of R against log P using the values from your table and draw a line of best fit. So, first thing, we'll take logs of both sides, we'll get log of R and log of P. Get 0.3, so I've done these previously on my calculator, so we'll get 0.3, 0.48, 0.6, 0.7, 0.78. Then we get 6, 5.86, 5.79, 5.72, 5.68. Alright, so that is just replacing what R is in the log calculator. Alright. So log P against log R. Logarithm used to manage and explore non-linear trends in data. As we can see here, P and R and then P and R. So we can now plot it and draw a line of best fit. That's what we've done. Use your graph to estimate the values of A and N to two significant figures. Well, we're told that A and N are constants, so we need to find the value of the constants. We actually need to rearrange the original relationship into y equals mx plus c. So, if we take logs, we get log P equals to log A R to the M. Use the addition law to break it apart, and then use the power law from the power down. And then, so the log of A is the constant from the linear graph, and N is the gradient from the linear graph. So log of A is 6.2, so 10 to 6.2 equals A, so A is equal to 1,600,000, or 1.6 times 10 to the 1, 2, 3, 4, 5, 6. So 1.6 times 10 to the 6 if you want it in standard form, which is also fine. So if N is equal to minus 0.67, so it's negative, which implies that P is equal to the 1.6 times 10 to the 7 to the minus 0.67, which is the final equation for this particular question. So that's the original data and the calculated graph. So it's not that far out, to be honest. There is a second situation that you may need to deal with, which is slightly different. Y equals AB to the x. In this case, the variable x is in the power rather than the power being raised to a power, if you will. So, take log of both sides again. We got log of y equals log AB to the x. Separate using the addition law, so we can separate that and break that apart. In the power law, bring the power down, and then compare with a straight line, and it's pretty much the same as before. Nothing's changed. Okay. Note that the axes we use for these will be different to the previous one that I've just used. Okay. So in this example, to get a linear relationship, we plot log y against log x. Alright, so for the first example, second example though, look, in this example, to get a linear relationship, we plot log y against x. Yeah. We're putting it against the x. You'll see why in a minute. ensure you check what form the equation is, as this will affect what you plot on your final x-axis. So the graph shown represents the growth of a population of bacteria P over a period of t hours. The graph has a gradient of 0.6 and meets the vertical axis at 0,2 as shown. A scientist suggests that this growth can be modelled by the equation P equals AB to the t, where A and B are constants to be found. Write down an equation for the line, part B, using your answers to part A or otherwise. Find the values of A and B, give them to 3 significant figures where necessary. Little words here, so we broke it apart and we've got the graph on the right. So we need to interpret the meaning of the constant A in this model for part C. So use the line above as a starting point. So log y equals log A x log b. So that's this up here. So use the variables in the question. So we've got log p equals log of A plus t log b. So just replace them. The y-intercept is log A and the gradient is log b. So get log p equals 2 plus 0.6t. So just substitute in. Okay, so right without the logarithm we get p equals 10 to the 2.2 plus 0.6 to the t, or times t. Separate using the index laws, so that's 10 squared times 10 to the 0.6t. Rewrite the right part as a bracket, so that's 10 to the 0.6 to the power of t. Calculate each power. So we get 100 times 3.98 to the t. And you can compare with the form suggested earlier on. So that means that A is 100 and B equals 3.98 by comparing coefficients. Okay? So we've got part A and we've got part B. Part C then. So interpret the meaning of the constant A in this model. So if t equals 0, we've got 100 times 3.98 to the 0, which is 100 because anything to the power of 0 is 1, so it's 100 times 1, so 100. In this case, the 100 gives the initial size of the bacteria population. And so, the meaning of A is the initial size of the bacteria population. And that's to get full marks for this particular example. And that is everything you need to know about the natural log and reduction in linear form. So please like and subscribe so we can continue this journey together and hopefully get to the end of the A-level course, which will start in September for lots of you. Good luck for those that are in year 13 and doing some final preparation to hand in your final exams. Best of luck to all of you and have a fantastic summer when I'm recording this. So if you're watching this, have a fantastic summer and I'll see you in the next video. Thanks very much.